Hello, and welcome to Yaka Digital Network videos. When you stand outside on a clear night and look up at familiar star patterns, like Akaso, it is easy to think of those points of light as permanent fixtures. They look like glowing pushpins stuck to a dark ceiling, completely unchanging. But those stars are far from permanent. They actually have a life cycle very similar to living things on Earth. They are born, they age over long periods of time, and eventually they die. Even our own sun operates this way. It is completely ordinary, just an average, middle-aged star belonging to a massive cosmic family of billions of other stars. Once you understand that stars grow and change, the night sky stops looking like a flat, static painting. Instead, you start to see an active, dynamic neighborhood playing out over billions of years. A star begins its life inside a nebula. Think of it as a massive space nursery, a huge, swirling cloud of gas and dust. Over time, gravity pulls this material closer together until the center finally ignites. It is common to think of stars as giant balls of burning fire, like glowing charcoal. But fire requires oxygen, and space is a vacuum. Stars operate in a completely different way. Let's look at a star's core. Deep inside, extreme pressure and heat physically smash tiny hydrogen atoms together to form helium. This reaction is called nuclear fusion, and it is the true engine that generates a star's intense energy. Look at these heavy, inward-pointing arrows around the outside. Throughout a star's life, it is caught in a constant tug-of-war. Gravity is relentless, always pulling the star's mass inward, trying to crush it into a tiny point. But notice the arrows pushing out from the center. That is the explosive pressure created by the nuclear fusion. The outward push of fusion perfectly matches the inward pull of gravity, keeping the star completely balanced and spherical. Our sun has been in this stable phase for over 4 billion years, providing the continuous solar energy that makes life on Earth possible. Before we move on, let's test a quick idea. Look at this flame. Which part do you think is actually hotter, the red part or the blue part? Take a guess. We naturally associate the color red with heat, like a hot stove. But in physics, the blue part of the flame is actually much hotter. This chart shows how that rule applies to stars. On the left side, blue stars emit high-energy light, meaning they are incredibly hot, often over 10,000 degrees. On the right side, the red stars emit lower energy, so they are much cooler. If we plot our sun on this spectrum, it lands right here in the middle. It is a yellow-white star, which tells us it has a medium surface temperature of about 5,800 degrees. Because color and temperature are directly linked, astronomers do not need to send a thermometer into space. They can measure exactly how hot a distant star is simply by analyzing the color of the light reaching our telescopes on Earth. Eventually, that steady supply of hydrogen fuel in the core begins to run out. When fusion slows down, the outward pressure drops, and gravity starts to win the tug-of-war. The core contracts under the weight, but strangely, the outer layers of the star balloon outward and cool down. Because the surface is cooling, the star turns red, entering what we call the red giant phase. This flowchart tracks that progression. An average star is born in a nebula and spends most of its life in the stable main sequence stage, right where our sun is today. As we follow the arrows to the right, we see the star expands into a red giant. Finally, it peacefully sheds its outer gas layers and leaves behind a tiny, glowing, tightly packed core known as a white dwarf. Notice the branch at the bottom. If a star is much more massive than our sun, it doesn't end quietly. It collapses violently, triggering a massive supernova explosion that leaves behind either a dense neutron star or a black hole. When scientists point telescopes at red giants and white dwarfs elsewhere in space, they are essentially looking into a mirror. Observing those older stars allows us to calculate exactly what will happen to our own solar system billions of years from now. So far, we have focused on individual stars, but out in space, stars do not exist alone. They gather together in massive clusters. When billions of stars, massive clouds of gas, and cosmic dust are bound closely together by gravity, we call that structure a galaxy. This model shows our home, the Milky Way. It's a barred spiral galaxy featuring a thick, bright central bar with sweeping arms spiraling outward. Earth and our solar system sit right here on the Orion arm, safely away from the chaotic galactic center. Mapping our position in the Milky Way gives us a true sense of scale. It shows us that our Earth is a small, specific address inside an incredibly vast, expanding universe. To trace the journey from start to finish, stars are giant nuclear engines born in clouds of dust called nebulae. Their color tells us exactly how hot they are, and depending on their mass, they follow a highly predictable lifespan. This ongoing cycle of gravity and fusion is the very process that pumps steady light and solar energy down to Uganda, keeping our planet alive. You can watch more videos for all classes here and get all content at www.yaka.cc.